Good evening, everyone. So semiconductors are ubiquitous. I don't need to tell you that. You walked in with your phone today, it's full of it. Perhaps drove in an EV car, which has more than a fair share of it. Even if you drove in on an IC engine, it has a fair bit of technology these days that is related to semiconductors. Certainly the way this thing will be transmitted home will be, the cameras are full of semiconductors. The way it will be transmitted to everybody is in the path, there is plenty of semiconductors. So I don't need to tell you that virtually everything that we are dealing with, even today, has a role for semiconductors in it. And this role is only going to increase, expand, and I don't know what the next word for ubiquity would be, but maybe it is uber ubiquity, and that's what you will see with semiconductors, I think, in the years to come. At the same time, the industry is going through a mega churn. A lot of the topic that we will discuss today is related to that churn, but it's being buffeted by change in underlying science. Both the physics and chemistry are changing very fast. The geopolitics is changing very fast. The investing and economics ecosystem surrounding it is changing very fast. And how all of that happens in terms of being put together might have to change at a rapid speed as well, given all the things that are going on in the world today. So a lot of what we will unpack is exactly that. Now, we cannot do justice to that complex a topic in 90 minutes. So if all of us together have piqued your interest to, one, study it, learn about it, and follow it as it evolves, then we would have done our duty today. There is no way that we can communicate, such a vast body of information in the middle of one of the biggest and fastest churns that is happening all in a short time. But I hope we can persuade you that it is worthy of your time and attention, and that you can actually look forward to it. Let me begin by saying the semiconductor industry is already very big. It's about $600 billion. It's going on to becoming, say, about $1 trillion by the end of this decade. To put that in context, the mega industries, the energy industry or the transportation industry or the food industry, are all in $5, $10, $15 trillion kind of size. So when you think of a semiconductor industry that's $1 trillion in size, which is operated on by let's say dozens of companies, not thousands and thousands, but hundreds of companies, against something like transportation or food, in which literally there are millions of companies around the world, you get a context of the scale and concentration, one versus the other. The other thing about the industry is that it is growing very, very fast. So the energy industry, as some of you may know, is growing, and should be growing even less if you were to listen to the COP27 that is going on right now, but it's growing at something like 1% a year. The food industry might be in the same very low single-digit kind of numbers. The semiconductor industry on aggregate probably grows in the low teens, and aspects of the semiconductor industry are going at 50%. So if you think about chips in artificial intelligence, for instance, I think 50% growth might be, and we'll ask Professor Murali about that, since he works on both sides of that equation. But I would suspect it's probably growing in the 50 to 75% annual growth rate kind of range. So aspects of it are growing very fast. So it's a very large industry growing at a fair clip. That's not a very common thing in the context of both science, engineering, and economics. What I thought I'd do is just introduce a few terms for those of you who might not be familiar with it. As I said, those of you who are experts in it will find this 101, but it's often useful to go to 101 every once in a while so that we have a good sense of where we are starting from. Please, when we do the discussion, after we do the discussion, we will have opportunity for Q&A, and we can take both tough and easy questions at that time. So the title is partly explained by the fact that a gentleman called Gordon Moore casts a somewhat big shadow on the entire industry. So Moore, in a fit of fancy, wrote in 1965 this phrase, that a number of transistors in a dense integrated circuit doubles nearly every 2 years. It happened a little bit like we always do in India, which is, he actually said it might double every year, and then he did the typical Karnataka thing, which is Solpa adjust Madi, and he said, okay, we'll do it every 2 years so it doesn't come back to bite me, and that's how the rule got promulgated at that time. He didn't even call it a rule. It became a rule many years later, and that's literally how we think of the growth of the industry. Now, in the initial stages of the industry, this had the inspiration or the aspiration that it made the company sort of try to deliver to this. One of the things that is happening in the semiconductor industry is that this rule has begun to hold a little less. It's beginning to hit the natural limits of chemistry, physics, and sheer size and power and all of those things. So we'll talk a little bit about some of those limits. It's not completely gone, so it's not unmoored in the technical sense. It's beginning the process of being unmoored, and hence the title. So maybe I'll work this from the right side of the page, which is, you all probably know sort of electronic components. Some of you might have seen the old radios and stuff like that, which actually had components that you could easily identify in size, and that actually, when put together, sort of made up that radio. So we've been making progress in sort of this direction, and the semiconductor sort of zone is a bunch of let me call them devices that are memory chips, logic chips, microcomponents, and then the analog computers. What analog computers do is that the digital ones essentially function with a sort of a 0-1 signal, whereas analog functions also function with a wave signal. If we have time at the end, and if some of the others want to talk about it, we can talk about how quantum computing is different from all of this. But the idea is essentially that the 0 and 1 gets captured in these semiconductors. By the way, I didn't say what semiconductors are. They are, if you want to think about it, they swing both ways. They conduct when you ask them to conduct, and they stop conducting when they don't, then you don't want them to conduct, and that's what you control through various devices. And that's why it's called semiconductor. So think of it as half conduction as the logic for why semiconductors are called what they are. So when we speak about semiconductors, essentially we are talking about chips and devices that are on sort of the left side of the spectrum. It's relevant to sort of note this because when we speak about India's role in this, we'll talk a little bit about where exactly India might fit. There are, of course, classifications even within the left side, which we'll get to in a second, that might help us understand where India might play a role in this. So I'm going to sort of build out, if you want to think about this as sort of a simplified chip making process. And what you'll see here is sort of the nub of the early stage of this is what is called design. And if you want to think about this, this is where a lot of brain capacity is used to design what it is that the semiconductor and the group of semiconductors in a particular array might help you do. And that's what is the first stage of this semiconductor chip making process. This is an important step because lots of the companies that are, and again, let me use an economic term, capital light, might engage in this kind of business where they're actually designing the chip rather than actually making the chip. The next sequel step to that is actually to make the chip. You actually make the chip in something called a fab. A fab is a place where you fabricate the chip. Now, you will see, and we'll introduce some of the companies that make this chip. Many of you have probably heard of Taiwan Semiconductor, or TSMC, which is obviously the largest fab for semiconductors in the world. It is based in Taiwan, and hence the geopolitics of this situation. Of course, TSMC is now being wooed to put in plants in other locations, including in the US. One or two of those plants are already up and running, and more are on the way. So there is sort of this evolving geography of semiconductors, if you will, and TSMC is at the center of this discussion about where exactly they should locate and how they should manufacture. They're also at the cutting edge, and we'll speak a little bit about exactly what that cutting edge is. It's a little bit like bell-bottom fashions, right? So the early stages of this was very precisely defined by something called nodes or nanometer classifications. But later on, these just simply became generations, one generation after another. So today, when we say that TSMC or Samsung is making 7 nanometer or 5 nanometer, just think about it as it's today's fashion that Samsung and TSMC are able to do. It doesn't perfectly correlate with a scientific backing to that number, but it is sort of a generational shift from the immediately prior one that took place about 2 or 3 years prior to that. And then the assembly, testing, and packaging, a lot of which today happens in China as opposed to Taiwan. And that is putting all of this together in a manner in which it is useful for a variety of devices that the semiconductors are placed in. So if you want to think about it, design, manufacturing, assembly, testing, and packaging is sort of the stages of the manufacturing process. If you want to think of it in economic value-added terms, roughly a third is at the beginning. Roughly another 30-40% is in the manufacturing part of this, and then the last bit surrounding the assembly, testing, and distribution is the remaining, which broadly speaking is a third. But if you specifically focus on the packaging side of this, is probably only about 10 or 15%. So that's how it stacks up. Now, for those of you thinking about this from India's supply chain point of view, you have to be organized in such a manner that you have things coming in and things going out at various stages of this in order to figure out whether you're part of the supply chain. So when people speak about trade in value-added and supply chain terms, they're essentially talking about how are you playing a role in various aspects of this in and out, so that you import something, you add value to it, you export it, and then the finished product might actually get finished somewhere else and then be sent to a consumer location that may have nothing to do with one of the early countries in that process. This is a little difficult to read, but this is the point I was making about these nodes in semiconductors. Suffice it to say, and we can again explain it a little bit more in the panel, that the cutting edge is now going from 7 nanometer to about 3 nanometers. And this is where TSMC and Samsung and others are locating a lot of their research effort. 5 nanometers is already in production, and 3 is definitely lab tested and so on, and could well be in commercial production in something like 18 months or so. But the opportunity set in terms of quantum is still in the middle. So when people tell you that we're thinking about fabs in India, and we can still debate whether that's a good idea or not, but when you think about fabs in India, you're essentially thinking about sort of the 28 to 50 nanometer, 90 nanometer, that band. You're not thinking about the absolute cutting edge at this moment. Now, we'll see later on where that will take us, but that's really the fab segment of India that we are thinking about as we speak today. There's plenty of demand for devices. So if you want to put a semiconductor in a fridge, for instance, the space demand is very different than putting a semiconductor in here, and a form factor which is getting smaller and smaller. A fridge size remains roughly the same if you want to think about it that way, and therefore the requirements of space and density are quite different for a refrigerator from a TV, from a phone, to this thing, which I didn't mean to show it, but this is actually got a couple of chips in it. It's actually something called an Oura ring, which measures your heart rate and various other medical parameters and literally there's many in there. You can see how big that ring is. So with that introduction, let me invite our sterling panelists, Professor Murali Annavaram, who is professor at USC. You can read his full bio as you can for everyone else, and is a visiting professor. It's our privilege to have you, Murali, at the Indian Institute of Science. His day job is a computer architect, but in that he takes a very bird's eye view of a lot of the things that go in related to semiconductors. So please. Professor Navakanta Bhat. He represents the further upstream of semiconductors. He's the nanoscience and chemistry and physics man related to the materials of what goes into all of this. So, Professor Bhat, welcome. Sanjay Palsamudram. Sanjay is actually from the industry, now an investor and an entrepreneur in the fabless space in India as well as outside. So we'll have that perspective as well. And then Pranay, welcome. Please. So Pranay is from Takshashila, and he has written extensively on the policy angle on semiconductors, particularly as it relates to India. All four of them, as is true of a lot of the science of semiconductors, all four of them have actually been in industry, because it's a little academic to speak about it purely from an ivory tower. So we are privileged that they have all actually got their hands dirty a little bit, and in that process, well, actually, I shouldn't use the word dirty. As you perhaps know, the clean rooms in semiconductors are the cleanest that people, even among the infectious diseases researchers, would actually be very proud of, to the degree of lack of dust that is in any of these rooms. So welcome, everyone, and thank you again. So rather than have each of them speak, what I'm going to do is just shoot a round of questions, and we'll just go through that, and hopefully we'll have about 30 minutes at the end to take questions. So that's sort of the format. And I'm going to begin on the science side of this, since we are we are privileged to have two professors with us. And I'm going to start with Navakanta, if I may, and ask you, just trace for us a little bit about the evolution of the, evolution of the materials that go into semiconductors, how that has come to sort of today, and how you might think about that now that we are beginning to approach some of the limits in both physics and chemistry related to these materials. So please.
Thanks, Narayan, and it's a privilege to be part of this panel. You asked a very loaded question to trace the history. Maybe I'll start by saying that this year is very special. The reason being, we are celebrating 75th anniversary of invention of semiconductor transistor. Semiconductor transistors have revolutionized the world, right? We take it for granted, but the invention of transistor happened on a semiconductor material called germanium way back in 1947. Easy to remember, the year when we got our independence. And this was at Bell Labs, right? Interestingly, silicon overtook germanium very soon, although initially some chips were made, mostly memories on germanium. But silicon was very, very unique. I often say that silicon is God-given, God's gift to humanity, right? It has amazing properties as a semiconductor, but also it has its brothers and sisters, such as other derivative of silicon, which is silicon oxide, silicon nitride, which is absent for many, many semiconductors, right? Such as germanium, gallium arsenide, and so on and so forth. So silicon today is almost, I would say, more than 90% of semiconductor electronics that we see. And very small portion is, niche application, gallium arsenide, for very high frequency RF. Germanium has made a comeback. Today's silicon chips are done on a material called strained silicon, which means it is not naturally occurring silicon. It's silicon which is artificially created by manipulating the atomic distance of silicon. And for that, we use germanium. So very little germanium goes in silicon, right? So oftentimes in the past, many years, many technologists had predicted the death of silicon technology and death of Moore's law. But the innovators in the industry have proved all of them wrong. So I would say Moore's law and silicon technology will continue at least for next decade or two, right? Having seen the history. But there are new materials coming up, right? Gallium nitride is a very important semiconductor materials. These are called compound semiconductors as opposed to elemental semiconductors, which come from group 4 of periodic tables, such as silicon, germanium. You can also make a semiconductor by combining group 5 and group 3. Gallium nitride is an example. That is going to play a very, very important role in emerging technologies such as electric vehicles. High power devices cannot be done by silicon. Similarly, the technologies of 6G and beyond, very high frequency, cannot be done by silicon. So gallium nitride is an emerging technology. Silicon carbide, right? Graphene was talked about. You had also mentioned that, graphene is a very, very interesting material. There was a lot of hype because of the Nobel Prize. But graphene is not a good material for making chips and transistors. Because graphene, although we are talking of semiconductors, graphene is called a zero band gap semiconductor, which means it doesn't have band gap. Strictly, it's not a semiconductor, right? So graphene is not a great material, but there are graphene analogs that are emerging. Just to tell you that emerging materials, what are called 2D materials, these are class of materials called TMDs, transition metal dichalcogenides. So a lot of very interesting materials are emerging. I think all these materials will complement silicon technology. Silicon will continue to lead, but others will also complement and help us take this Moore's law in the next decade or two. Let me stop there and I can come back.
Thank you very much, Navakanta. Murali, if I may ask you to take the engineering side of this, there's a revolution I understand that's going on that is switching x86 to ARM kind of architecture. So could you tell us a little bit about how we got to this little fight between x86 and ARM and what you think the growth path from here? And again, we apologize for the jargon, but difficult to talk about the future of the industry without it. So we'll keep it simple, but you'll have to listen to a little bit of it. So,
is it done? Is it working? Okay. So, so to kind of connect from where Professor Bhat mentioned, once you have the materials kind of selected, all these systems need to be programmed. Otherwise, they're useless. And in order to program, basically you need a mechanism or sort of an interface where you tell, here is how you do an add on this machine. Here is how you do a multiply on this machine. And that's what we call instruction set architecture. It's again a jargon, but it just simply means that it's a contract between a programmer at a software level and the hardware that is built with some of the materials that Professor Bhat mentioned. And for many years, there are different kinds of architectures that existed on the planet. IBM, for example, Sun Microsystems, if you heard of those names. But over time, x86 became the dominant architecture in the world. Basically, every laptop you touched, every desktop you touched, every supercomputer you touched, all used x86. x86 was originated from Intel. Intel is sort of the big holder of the x86 ISA and also AMD. But part of the challenge is that x86 is what they call very complex instructions. There are instructions that can do really complex things with just a single instruction, and that becomes very difficult from a performance and power standpoint. And so what happened over the last, I would say from around 2000, is we were very much centered on frequency, like increase how fast you can clock them. Around 2000, people looked back and said, my God, this thing is burning down the house. And so power became a big part of the design constraint. Today, if you look at chips go and succeed from a power perspective, because we are used to, or we are addicted to actually, to our mobile devices, whether it be our phones or our laptops or other kinds of devices. And that's true even in the largest data centers in the cloud. When Amazon is using these big data centers, they're churning down millions of dollars of electricity bills, and they don't like that. So they want to also cut down. So across the space, power consumption became an issue, and hence ARM, this machine that you mentioned, ARM, it's a company based off of UK, which has been designing a certain kind of instruction set architecture, which allows us to kind of tweak some of the power consumption metrics a little bit more efficiently. And when companies that are highly vertically integrated, such as Apple, put in their resources into taking that ARM processor and building it in their own in-house design, and putting some of the best people in it to actually make it very power efficient, suddenly ARM becomes the most popular architecture in the world. In fact, every cell phone today, I can't imagine that there's a cell phone that's actually not based off ARM processors that you're actually using. And so ARM became the de facto standard for your cell phones. But it's not going to stop there, because the cell phones today were the laptops of the past, right? I mean, basically, you're sort of eating into it. And so now you end up in a scenario where you have huge computing systems that were built out of x86 are slowly drifting towards ARM, or you can think of it another way, the ARM is kind of eating into them. So the M1 chip, which is the Apple's most recent M1 and M2 chips, they are based off of ARM instruction set architecture. So in fact, if you buy a new Apple laptop, it comes with an ARM instruction set. 2 years ago, it was x86. That's because the power consumption can be finely tweaked and tuned in the architecture associated with the ARM ISA. And so as a result, the desire to reduce the power consumption made ARM a more favorable architecture over time. And as a result, now you end up with Apple pouring $1 billion into the design that Narayan mentioned. And now you get these really very, very power efficient designs. And it's amazing how much they can do for a single watt of power that you provide these systems. And so the shift really is driven by our desire for running long. I remember in 2000 when I was working at Intel, one of our holy grail of ambitions was to have a cross-country flight between San Francisco and New York without recharging your laptop. But nowadays, nobody even thinks about it. I can come from US to India and back on a single laptop charge and never have to recharge it. And that's because of this drift towards the power consumption. So that's really the reason why now you have a lot of systems that were primarily phones. ARM started with phones, now it's going into laptops. Sooner or later, you will see ARM-based servers. And so there is a reason for Intel's and other x86 companies to be worried, because they have to kind of compete at that power metric, or the power consumption metric.
Thank you, Murali. Just hold that thought. So we've now got two major sort of drivers of change in the semiconductors, one coming from the science, pure science of it, and then the second coming from this design and instruction set that Murali spoke about. Let me shift, Sanjay, if I may, to the third set of drivers that is actually moving the industry and churning it a fair bit. And this is the question about applications, and applications to AI, EV, IoT, anything else that you want to add. So please take it.
Sure. Good evening, everyone. Before I start, I thought I'll have a quick idea of how many of you in the audience are from the semiconductor industry. So I know if I'm talking to somebody who is already familiar and who is not. Okay, very few looks like, okay, it's a minority. Okay, so there are many technology trends in the industry today. If you talk to a Dunzo guy or a pharma guy, to anybody, they all seem to know machine learning and artificial intelligence. What it is different, but you take any startup, no matter which industry, they somehow want to plug in AI, ML. AI, ML has come in. From that standpoint, if you were to actually see the value of the entire technology stack, When I say technology stack, it means the chip, the embedded software, the actual software that sits on it. If you see the value of it, if you take a cell phone, perhaps you can argue it's definitely less than 20%, maybe 10 to 15% of the value of the cell phone is derived with semiconductor in it. The rest of it is either the display, the software, etc. But if you take artificial intelligence by itself as a technology, 40% of that entire technology stack is derived out of semiconductors, at least it's envisioned as of today. So if you imagine that AI is going to ramp up in the future, because every industry, everywhere you'll talk about AI, ML, the trend along with AI would mean semiconductor value into that trend is taking a significant share. So if you were to extrapolate that way, whether it is AI or EV, electric vehicle, or even IoT sensors, there's a lot of IoT related growth. So if you take semiconductor value in that, it's becoming more significant than the traditional applications like computing industry or telecom industry or cell phone industry, etc. So from that standpoint, not only that semiconductor technology is evolving and growing rapidly, I think it's a positive feedback loop with AI and other application trends growing. It's going to drag semiconductors into a lot more growth as well.
Yeah, if I could add to that, if I understand your point correctly, that if you think of an internal combustion engine, even the most advanced of them, probably has, I don't know, let's say $500 of chips in it. But an EV car probably has $5,000 of chips in it. So it's a very different scale that the electronics broadly and semiconductors in particular play in this evolving set of use cases. And I don't think you mentioned 5G, but if you...
Oh yes, 5G as well.
So if you add 5G to this mix of evolving trends in use cases, I think that adds another layer of why. And then let me come to the mother of all changes that's going on with Pranay. So tell us a little bit about sort of the geopolitics of this and how concentrated particularly the manufacturing side of this is, and why that opens us up to a significant geopolitics discussion that will then require response of the type, and we'll get to the responses in a second, but please.
Yeah. So there are profs on the stage, so I'll try to steer away from the technical side so they don't find out I'm an imposter. So let me try. Okay, so first thing, Narayan, as you mentioned, so first of all, the diagram that was shown, it shows how this industry operates as a global supply chain, right? There are multiple suppliers. I don't know, last count, Intel had some 16,000 plus suppliers. There are various parties doing small part of the supply chain. So it's not a national industry as steel is probably, right? So it is spread across the world, and every company or country has specialized in some part of this supply chain, and they have gotten really good at it. And that's why, as Professor Bhat was mentioning, that Moore's law will probably still say, because a large contribution of that is because of this supply chain. TSMC does very well in just manufacturing, US does very good in design, Indian design centers in India also contribute to design. So it's sort of spread across, and each part does small little bit of it, and then you have the chip coming out, right? So there are multiple trips that the chip makes across the world before it becomes a reality. But now, so it was operating all fine until the world order was conducive to it. But now the world order isn't, right? And now, given that technology is being perceived as a significant chunk of national power, and semiconductors underlie any of the things that we are talking about, future technology, it's suddenly sort of being weaponized in a way, right? And precisely the reason why this global supply chain actually produces very cost-effective, cheap chips is also the reason why it can be used as a geopolitical weapon. Because as I said, it takes a lot of capital, etc. So there are few countries and few companies which can specialize in it, and that means there are choke points. So if there are choke points, you can sort of stress at it. So there is a Willy Shih at Harvard Business School has a very nice statement about this. Think of it as a transcontinental relay race with hidden hurdles. And countries can put hurdles in front of other countries or companies in order to do that. So it was fine until the world order permitted it, but now given that things are different, we are in that region where this particular aspect is being seen as a core thing to national security. And when it gets seen as a core things to national security, a few things happen. One, government start giving subsidies, there's industrial policy, and it might probably crowd in some investment as well from other places. But every government in this sector, from Taiwan, even the settled players like Taiwan, Japan, South Korea, are having one industrial policy or the other. So everyone's in this game. The attempt is to localize a bigger part of this supply chain. So think of it, if they are operating only at one part of that diagram, they want to capture 2 or 3 of those, right? So that's sort of the idea. So that I think is a tailwind. I think that there will be more money coming into this sector because of that reason. And there are various applications like we just discussed, which will come in, and that will also drive the reason. One quick thing about what are some headwinds, I thought I'll just mention. The same thing which I said, perception that this is core to national security is also a headwind, in the sense that because countries are now thinking this is really important to us, there are various things like export controls, you might see limitations on human movement, you might see investment screening controls. We are already seeing that, in fact, right? So there is a risk that this globalized supply chain, which was the reason for its success and effectiveness, might be affected because of this geopoliticalization of sorts. So I'll stop here.
Terrific. So just to add to Pranay's point, some of you may have missed it, but there was this saying that Biden did in one weekend what Trump couldn't do in 4 years, when he essentially revoked the ability for American semiconductor engineers to work in China, and they all had to return about a month ago. So it was a pretty body blow to the semiconductor industry in China, and it's clearly politics and geoeconomics at play in that specific context. But there have been many regulations, acts, the US CHIP Act, for instance, the European Union CHIP Act, that have come into play. So let's talk for a quick minute about the total amount of money that this, everybody says it's very capital intensive. I'll just introduce a number and then any of you can pitch in. Just to give you a sense, the US CHIP Act has sort of a 75 billion kind of price tag on it. Taiwan Semiconductor's 2023 capex is similar order of magnitude, maybe 75 to 100 billion dollars. So one company has a capex that is equal to the United States' new shining gold program called the US CHIPS Act. So it takes a lot of money to get into this, particularly the manufacturing side of this thing, which is where I think a lot of the debate on India will center, and we'll get to that. So I don't know whether you want to add further, Sanjay.
Sure. If you look at all the industries, I think pharma companies, perhaps the only other industry which is spending a lot more as a percentage of sales towards their R&D. Perhaps second to that would be semiconductors. If you were to look at US, 20 to 25% of their overall sales is spent towards R&D, and maybe around 20 to 25% towards capex. But that number is very different for TSMC because it's a manufacturing juggernaut, and I think 70% of their spending is going to be on capex, and that is towards manufacturing, and very little as a relation to their spend on capex would be towards their R&D, maybe less than 10%. So from that standpoint, depending on where you are in this global ecosystem, your focus would be to spend on that so that you become an expert in that, and that's how you are contributing to the global supply chain, and that's how the overall cost to the consumer has reduced. I think BCG did a study. If you do not want to depend on this global supply chain, and if you want to be an independent country which is completely vertically integrated, not dependent on anyone else, that particular country should spend $1 trillion to start with and spend another 100 billion every year to be independent, which would translate to perhaps at least 65% more for the same product that you want to buy. And it's unsustainable. So this mutual interdependence is so strong. You can't live without others, and you have to live with them. So you have to figure out a way. And it's not an easy solution because of the politics, geopolitics, economic power, military safety, everything is completely integrated and intermingled. So this CHIPS Act from the US is, I mean, why not put more? But then you're going to tip the balance elsewhere. I think there was sanctions from the US to make sure ASML, which is producing this EUV technology for lithography, which is very essential for 7 nanometer and below technology, to not to be shipped to China. So there is sanction against it. So there are many different ways they are throttling to control advantage. At the same time, you cannot cut them off. If you need a rare earth metal which is coming from, let's say, China, and you're interdependent again. So it's a very complex factor, and this will continue to be there. Each country is going to try to maneuver and see how they can leverage and modulate as time progresses.
Maybe I can ask, since you mentioned this machine called a lithograph, maybe I can get Navakanta to tell us a little bit what this machine is. This is a machine that is produced by this one company in the middle of Europe that costs each machine roughly about $200 million. So just tell us for just a little detour on this one EUV machine, which is sort of the standard, the gold standard now.
Yeah, just to sort of, again, given the diversity of audience, the show of hands said only few hands went up. So lithography is essentially a technique of printing the design. The design is what all these design engineers are doing on their computers on how many transistors will be in a chip, let's say 1 million transistors, right? So where will they be placed, which is called placement, and how will they be connected? That's called routing, placement and routing, right? That's what the designers are doing on a computer. Now you need to convert them into what is called masks and print that on the silicon wafer, right? That is how the design gets translated onto your chip. So it's a printing technology, simply put, right? This printing, of course, is not done by the printing press that you see for newspapers, but it is done with a machine called lithography machine. It used to be done using a lithography machine which would have ultraviolet light, UV light. That's why it was called UV lithography. Wherein you would use UV, which is, a light with wavelengths in a few hundred nanometer. And we started bringing that wavelength lower and lower, right? And in fact, lithography technology itself has gone through a whole range of, transformation, right? We actually call lithography today as we fool photons. Photons are elementary particle of light. What you see in mask and what you print are completely different, right? So that is how complex the lithography has become. So EUV essentially stands for another big machine, which stands for extreme ultraviolet lithography, which essentially means that the wavelength of this light that you're using is so small that the conventional optics of lenses doesn't work there. You really need different kinds of optics there. Right? That's why these machines become so expensive, right? So that is going to become a very crucial technology to print these chips on silicon going forward.
Maybe I can give the metaphor to the textile designers and the bird watchers by saying it's the ikat weave of a small bird, all done by hand, and you have to pay a lot for the fabric that comes out. That's literally what the lithography machine does. Of course, it does it with bombarding, I don't know, tin or whatever it is in the lithography machine to make the ultraviolet ray show up on the wafer. Anything you want to add to this economics component? No. Okay, so let's sort of move to India's evolving role in this. The logic for India to even think about this is the geopolitics of this, and particularly the geopolitics surrounding China and Taiwan, and they all hold a very central place in this. The other countries have different reasons to approach the same problem, but of course they approach it differently given that they might have different views and relationships with China. And this includes EU 27, it includes the US, Japan, Australia. Everybody has a particular view and angle on this and how this is going to evolve, and each of them is charting a course forward that could look broadly similar yet intricately quite different one from the other. So let me start with the design side of this, and maybe I can start with you, Murali, and then Professor Bhat. There's a lot of discussion about the Indian skill in the design side of this, because it is, if you want to think about it, closer to the DNA of software. It is capital light. We already have engineers embedded in the, and some of whom are represented on the panel here, embedded in either the Intel KPO or the Qualcomm or NVIDIA, all of these centers that we already have in India. They are, even at this very moment, contributing to IPs and patents that those firms are publishing in respective countries. So is there a role from a talent, engineering, contribution point of view, and maybe I can get Professor Bhat and Murali to answer this question about, is that a good role for people to play in India? And then we'll go to the ecosystem role with Sanjay and with Pranay.
Yeah, so when you look at the chip design, for most of you, you've heard of software and outsourcing and the Wipros and the Infosys. But there is equivalently heavily software-centric role in the design of the chip. So the design of the chip, vast majority of the time is actually spent not in the fabrication. The fabrication is literally minutes, right? Like you can churn out a wafer in no time. But to what to put and how to route and what to do is all done in computers. In fact, vast majority of the design effort is in software. So there are tools that Synopsys, Cadence, and other companies produce, which allow a designer to say, oh, I want to achieve certain power goals, certain performance goals, and then you go back and tweak it and turn it and tweak it and turn it. And so substantial software effort actually is required for this design. And as a result, if you heard of the word fabless design as one of the common terms you may have heard in industry, it means that I don't have a fabrication facility to actually put those masks and print it, but everything up to the print. So it's like the newspaper analogy that was given. Think of this as the guys and the girls who go and get the articles and frame it up and get it out, which one goes onto the front page, which one goes onto the center page. All of that has to be done before the printing actually happens. That is the fabless design. The fabless design is basically allowing you to take a particular end goal in mind. Let's say you want to accelerate image processing. So you have to build a chip to do this acceleration, and all of that is done using fabless design. And now, once you have that design in a particular format, then you send it to TSMC or any of these fabrication facilities, which will print it and send you the chip back. Now, this tends to be that there is a lot of human labor requirements in this particular design process, because let's say you designed an addition module for the simplicity of discussion. Let's say you want to do an adder. How do you know that when you design an adder, it is going to work correctly? So you do 2 plus 3 and it's equals to 5 and you check that it is in fact 5. And so there's a lot of testing and verification that goes with these fabless designs, which is why if you look at most of the Indian hardware industry people, they tend to be very much oriented towards verification and testing. Because for every single bit of architectural work that is done, think of it also, there's a lot of analogies to like building construction too when it comes to this, right? The architect, that person will design this fancy building, and the guys and the girls on the street have to spend hours and hours to get it right. And that is verification and testing, is to actually make sure that it actually works. And so in an Indian context where a lot of the verification and testing has come here as part of the design process, because labor-wise, it is still cheaper, even though Bangalore housing prices don't make you think of that way, but it is actually still relatively cheaper to have a design verification team be in India where there's a large number of people who can actually work on it. Now, the flip side of it is that we also, these machines that Professor Bhat mentioned are so expensive that it's impossible even for an institution of prestige like IISc to own a couple of them. It's not possible. And what that means is that all the students that we churn out, they have very little actual lab experience. They don't actually know how to take a chip and do bench testing. They just don't, because we don't have the facilities in any of the academic institutions to actually train that. So as a result, it's kind of a chicken and egg problem, because we don't have the infrastructure to train people to do bench testing and lab testing. And so we tend to be very software oriented, and we know how to do software. And a lot of the universities in India are very good at teaching logic in software, but not so much when it comes to let's get our hands clean, in this case, as I said. And so getting the hands clean is a really difficult task. And so as a result...
Having clean hands are not an Indian DNA in general.
Yes. And so it's a really difficult problem to come down that hierarchy to get to the fabrication piece. And as a result, what I'm afraid is the reality of the Indian hardware industry is that we will tend to be very much centered for the next several, maybe a decade, still continue to do fabless design where we are only looking at the software aspect but not actually on the manufacturing side of things.
Professor Bhat, maybe you can pick up there, and also, and both of you, I'd like to ask you the question. So that's industry. What role could academia play as well?
Yeah. So let me continue from where Professor Murali left. He mentioned about this fabless design and fab, right? I just want to tell you that when semiconductor started, the companies were vertically integrated. That is, the same company will do design, fab, test, everything, right? But in 80s and 90s, this partition of fab and fabless happened, right? Then everybody thought, oh, don't worry about manufacturing. Anyway, there are folks who will do this foundry. Just focus on design, right? But I must tell you that there were a small set of people, although not in majority, right, who always believed that that's a very bad idea, right? For any country for that matter. India, of course, right? It's as if asking, do you need armed forces? It's a no-brainer, right? I mean, you need army, navy, everything. Just like that. Do you need manufacturing? It's no-brainer. Because today, the threat is not physically somebody, crossing the border. The threat is somewhere else, in the current, information revolution that we are going through. The threat is through these chips, right? Where do they get manufacturing? Is there a malware in the chip? And so on and so forth, right? And rightly so, the government had also recognized it. And in fact, 15 years ago, Government of India, Principal Scientific Advisor back then, had set up a committee to come up with suggestions for setting up semiconductor manufacturing ecosystem in the country, right? I happen to be a member of that, and Madhu Atre, who is sitting in the audience, was, industry doyen here, was also a member of that. And we submitted a report clearly articulating that this must be done in the country. And we actually suggested that, getting into bleeding edge technology is very difficult. You have to start somewhere. In fact, solar was a great idea back then. In fact, at that time, many successful solar companies were there, including Mosabayer and, But of course, Chinese dumped everything, and as was mentioned here, everything was sort of contracted out to China, right? And that's how, the solar industry, which was doing extremely good, went down, not just India, everywhere else. But now there is a revival that is happening, right? So when it comes to manufacturing, I think it's no more a question, right? We have to have that. And in fact, about 10, 15 years ago, government decided that they want to set up centers of excellence in academia. You asked the role of academia. Today we have, for instance, facilities in a few select institutes, including IISc, a nanofab, for instance, which I would say among the top 10 anywhere in the world. People from Stanford have come and they have said that, the fab facility at IISc is better than what they have, right? So it can be done. We have showed that it can be done in academia, right? Now we have to show that it can be done in industry as well. The only difference is that the funding that is required is orders of magnitude higher, right? And that is where, we really need to figure out through government policies, how will we make that happen, right? There is the India Semiconductor Mission, as you know, it's a $10 billion mission as opposed to 50 or 60 billion Semiconductor Chips Act in the US, but still that's a very welcome step. I think the signals are in the right direction. Maybe you can elaborate more on that. But I think we need to do that. There is no other choice.
Yeah, just to add a couple of more points related to this discussion. So, yeah, the policy, I'll just briefly mention what the Indian government is doing on this, right? So, as Professor was saying, the government has been trying to build a fab many times. In fact, we have a fab which was under Department of Space in Chandigarh now, SCL. But there have been many previous attempts to start in industry as well. In 2000s and in early 2010s, we had attempts. But all of them couldn't fructify for one reason or the other. And one of the reasons for that, and Narayan, this comes into our territory, it's difficult to do business in India, especially when you are putting so much capital in, and the first chip that you will produce out of this will only be 5 years after, 3, 4, 5 years after you have even promised that investment, right? So it is, there is a lot of you will make money after a long time, so the gestation period is high. So the companies need to have full faith in the government policies, in what government direction is, tax environment, trade environment, and that wasn't the case, right? And there were also things like retrospective taxation and all, which threw things off gear. So this time, what is different from other previous attempts is, one, the policy is to build an entire ecosystem and not just a fab. So that's one major difference. So they are not just trying to build a fab, but there are also incentives for design companies, incentives for assembly companies, and incentive for a display fab also, so mobile phone displays, etc. So that's one difference. The second big difference is earlier the fabs, earlier the fabs were promised money which would come at a later point of time. So think of it as a production-linked incentive, sort of, where once you start production, you start getting money back. And that was not acceptable to a lot of companies because, again, uncertainties, why should I do that? So this time, for the scheme for assembly, for the fab, both promise upfront capital investment. So if you're putting 1 rupee, government is ready to back another rupee for fabs this time. So that, from the conversations I have had with some of the people in the fab thing, they thought this was a big move, and I think that showed a way that this time it's a serious attempt, and that's why they would probably be more interest, and that's why we're seeing some interest. So that's one, but I would say that probably there are 3 companies or 3 consortiums sort of which have come together for this fab, and probably, with good luck, we will have 1 fab probably, right, 1 or 2. But still, that wouldn't mean that India will be Atmanirbhar in semiconductors in any way, right? Even 10, 15, 20 years later, we will not be Atmanirbhar, we'll still require some chips from other countries. So interdependence is still a requirement. What I say is multilateralism here is a necessity and not a choice. So that will still be there. But coming to the design thing, that's where really India's comparative advantage also is, right? So think of it this way, like just like Silicon Valley started with Fairchild Semiconductor, Bangalore's Silicon Valley also started with a semiconductor design company, right, with Texas Instrument starting operations here in 1985. And the thing is, since 1985, there have been lots of design engineers who have seen many cycles and many full design cycles. So it's, while it started with probably outsourcing, but now there would be people who would have spent 30 years knowing the architecture, etc. well. So out of the 10 design, semiconductor companies by revenue, top 10, 8 have design houses in this city, right? So that's the extent of India's contribution here. So I guess, but the challenge is that the IP is not owned by Indian companies. A lot of these firms are outside India. So I think that's the next stage of maturity that the Indian ecosystem would like to achieve. So the government scheme is also there for design, which tries to incentivize the software, which Professor says it's very costly, licensing is very costly. So the scheme now has some incentives for that. So those are some of the attempts which are being tried now.
Sanjay, I'd like to ask you, Sanjay, I think if I'm right, actually built and sold a chipset company among the early ones in India. So he's actually a successful entrepreneur from this city. So tell us, is the ecosystem of these fabless and chipset companies in Bangalore evolving? Is it a bright spark? Is it the beginning of a spark? Where are we in this? And as a venture capitalist now, do you see that money is beginning to even think about India as a fabulous place, not a fabulous place, but for this? Yes.
The destination is far away, but we have many steps in the right direction. Especially with the new policy announced by the government, there is seriousness. Incidentally, 15 years ago, I met with Mr. Bhat regarding the same policy that was recommended to the government. So we've been seeing it since then. Now, purely in terms of ecosystem, there's clearly an advantage within India when compared to the other aspects of the ecosystem, design side, by virtue of many of these companies having design centers in India, there is that knowledge. The main issue we see is that the venture capital ecosystem is not yet fully either bought in, or they don't perhaps necessarily understand this deep technology enough to be able to take risk. They're willing to perhaps spend $1 billion on an e-commerce which is loss-making for maybe 10 years, no issues. But they will have difficulty to put $100 million into a very deep tech semiconductor company. And I'm just living through that right now. We are building a artificial intelligence microprocessor edge inferencing chip. And the difficulties we go through in the process of fundraising is monumental. So while there are many steps in the right direction, I honestly don't think the entire ecosystem is equally mature yet. But you have to start somewhere. You have to have a few failures to have possibility of a success. If you don't learn from your mistakes, you'll perhaps never have success. And this is not something you'll have the chance of first time success. So all these are a few steps in the right direction. And I'm actually hopeful in the future we will be able to reach that stage sooner than later. When we build fabs, it doesn't mean that we have to build cell phones and we have to export to other countries. We have such a large consumption in India alone. Even if it's just LED bulbs, 50 crore we need to manufacture. We buy those chips from China today. And you don't need advanced technology to build those chips. If you can actually build those chips in India, in the fabs which are being planned in India, can be consumed in India, and use that as a mechanism to build the ecosystem and graduate to more advanced technology, so that you're not only in a position to manufacture and consume what is required in India, but you're in a position to actually export as well. So that's the goal. It's going to take, I'm sure, several more years, but I've never been more encouraged than right now than when compared to in the past. So keeping fingers crossed, and hopefully we will take many large strides towards that direction.
Thank you. Maybe with that, I can get people to ask questions while you're thinking about your questions. And
hello. Hi. My name is Amit. Just to give you a kind, I came a bit late, so I don't know all of you. Sorry for that. So 15 years ago, I was the EA to the president of Videocon, heading their European operations, and I bought one production line for flat panel displays for NEC in Tamagawa and moved it to Italy. My plant was in Italy in Europe. And I bought one production line of plasma display panels from Chunghwa Picture Tubes in Taiwan and moved that to Italy and got the commercial product out and was selling in 9 countries in Europe. And I was 26 years old. And my dream was to get semiconductor manufacturing into India. And I told Pradeep ji, my boss, the owner of Videocon, that this is my dream. I want to build this. So he laughed. He said, it's on the way, raste mein. So then I moved to Vedanta. It's a metals and mining group. They have an arm called Sterlite Technologies, where I was with Ankit Agarwal. I got the chance to pitch to Government of India to incentivize semiconductor manufacturing in India. And I met Mr. P.K. Narotra, the Principal Secretary, Department of Information Technology, and gave industry recommendations with India Cellular Association and India Semiconductor Association jointly that, I had a budget of $1.2 billion US, money in hand, and I'm going for policy recommendations so that I can start. And there was such a, the response was that, bro, you're in a hurry. It's going to take some time for us to catch up. And so
may I interrupt and just get you to ask your question?
Yes. So the question is, right now, in the ecosystem that we are thinking of, envisioning of building, I have a lot of investor connects because now I'm in e-commerce. I have a lot of deep tech connects because I'm an advisory with a lot of deep tech. So in the ecosystem that we are thinking of building, including, let's say, photolithography and all of that on the wafer, the investments should enter, because the previous investment wave that entered with mobile phone manufacturing was only into bonding, was in the TCP/IP bonding with the PCB and the display. Now, where do you think the investment should start for us to just kick off based on the policy recommendations that we have received from the Government of India? That is the question. Just to point of entry for us to put in the money and start generating revenue. For semiconductor manufacturing to start in India? That's the question.
Go for it, yeah.
If the criteria is to see revenue quickly, then it's packaging, assembly, and test. Okay?
Okay.
Because to build a fab, one, you need a lot of investment and time. You cannot accelerate that. If the criteria was to really get to entry point so that you can make money and see revenue, then it's package, assembly, and test. Design is not really revenue. You have the skill which is necessary for the entire ecosystem. But if you want to actually generate revenue, then it would be that if others want to.
Can I get you to come, sir? Next one.
Yeah, bye.
Thank you.
Please
answer while it's coming.
So absolutely right. Like we discussed, the assembly thing requires cutting edge machines, but that is upfront investment. After that, it is labor intensive process. Again, a comparative advantage for India. So currently, a lot of this assembly happens in Taiwan and China, and there's no reason why it can't happen in India. So yeah, absolutely agreed.
So that's the point of entry. Okay. Thank you for that.
Hopefully you'll do it, and you'll prove us our optimism right. Go ahead.
My name is Atul Joshi. I'm sorry. My name is Atul Joshi.
Even closer, please. Sorry.
Closer. Is it audible? Yeah. My name is Atul Joshi. I have good two my colleagues. We work for Infinera. We are in their ASIC group, and we make chips for optical communications domain. My question is to Professor Murali. He alluded to x86. He alluded to ARM. I don't know why you missed RISC-V. So, I mean, whatever humble understanding I have, it is democratizing processor development, right? That is one thing why you did not allude it to, and if you can allude it to some place. And second question consequent to that, we have some implementation. So you have Shakti series of processor from IITM, and then you have, I think, Vega from CDAC. Where we lack, and compared to Sci-Fi, I mean, you look at Sci-Fi series, they have huge product line. So if you can give us some indication where we lack, why Shakti and Vega is not picking up as compared to Sci-Fi, and what skill sets we need to develop in order to catch up to that level. Thank you very much.
Since
Yeah, but
Narayan,
he answered my question directly, and I was challenged by trying to keep the jargon low, that's all. But
Okay,
otherwise, we would have definitely gone to, and it's on my page. I just refrained from it, that's all.
So there is, for those of you who are not as familiar, basically ARM is a licensing company based in UK. So if you want to use a processor built with ARM instruction set, you have to pay money to this UK company, and quite literally they'll give you a book, but it'll cost you $10 million to get that book, right? I mean, that's, I may be exaggerating, but it's not too far of an exaggeration. And so what RISC has done, which is a different kind of an instruction set, this is, it's for free. Here is the book, it's for free. So I think that's its strength and its weakness, because free is not as attractive when you're trying to make large number of products and huge amounts of investment, because you're always worried on the back of your mind that is this going to evolve with time? So for example, things like security, which is a big deal. ARM actually continuously is evolving to create new kinds of instructions that makes securing your processors very efficient. And same with x86. So because they're in a race, and so they're actually adding these features such as security, remote management. There are all kinds of other capabilities beyond just the standard add and multiplications that I gave as an example. And so one of the things that RISC-V has to sort of evolve into is, can it evolve with time at the same pace as ARM and other investments go through? So again, this is the problem here is that since it's free, there are not as much investments coming in from an external entity, because people who are building, as you said, the Sci-Fis and a few other companies, it's just not enough ecosystem to actually make a big dent to sort of push this RISC-V over its hump. And on top of it, to be also fair, ARM, if you are making a lot of chips, a $5 million initial payment to ARM ISA is not such a big deal, right? I mean, the cost advantage between RISC and ARM is that initial payment to the instruction set. But if that is not such a huge cost, it's not such a big deal. There's a lot of ecosystem support. If you write code in ARM, there are compilers that compile it instantaneously to your chip, and it makes it work very efficiently. So there's a huge software stack on the back end that helps when you write something in ARM. That's the reason why cell phones, whether it is Android phones or Apple phones, you write a software at the top layer, there's compilers, whether it is the Apple compiler or the Android compiler, that brings it down to the ARM ISA very very quickly. So that's the level at which you have to get to for the RISC-V, which is not there yet. And the advantage is really, if you were saying that the RISC-V has a big advantage, that advantage is really small. I mean, you know, ISA licensing few $1 million, okay, I'll pay for it. If I'm a really big company, I'll pay for it, right? And that's the reason why you have to sort of think in that context.
So correct me if I'm wrong, the software analogy would be fully open standard versus Red Hat versus Microsoft.
Correct.
Right? Where the Red Hat comparison would be with ARM, and the fully open standard is
the RISC-V.
Yeah. So, and the software movie is before us, so you can pretty much see why I think Professor Murali is speaking like that. Professor Bhat, anything to add to that? No. Okay.
Thanks. I'm Arvind Tiwari. I used to run the IoT forum for TI Bangalore. So my question is less about the hardware manufacturing, all that. The question is of the pull-through in demand. I'll give an example. NavIC is the Indian GPS chip, but it has a different radio band than the other one. So the existing chips don't support it. And the government has been busy. I mean, I was there in a committee that there is a subsidy that you need for the gap funding. And they have had to make it mandatory because very few manufacturers will add that radio because of the Indian demand is large. So the question is, what is the pull forward in demand so that the manufacturing will actually produce the 40 to 50% margin? Because you have to keep regenerating your fab. It's not an end capex. So where is the push forward pull for all these things?
I think you have hit it on the nail. This is absolutely essential. Again, let me go back and when the semiconductor...
Just paraphrase the question because I think some people may not have followed the question.
Yeah. So the question is, you may manufacture a chip, but unless there is a pull, there is an end user, it becomes very difficult for you to sell the chips. That is essentially what he was referring to. And the example that was given was this navigation system, right, that ISRO is pioneering, and that's in a particular band which cannot be accommodated by existing chips. And hence government can say that, look, we can have our indigenous chips and support that. There's already a pull by the user, which is ISRO and all others can take it forward. One of the reasons why we have not been very successful, we talk about success story in automobiles, right? Maruti came in and we are a force to reckon with today. But semiconductor technology, the Moore's law example, it changes every 2 years. You have to be at the leading edge, otherwise, you're out of the game. When the technology started with germanium, in fact, India was at the forefront. Bharat Electronics was at the forefront, not too far behind. And TIFR at that time was also at the forefront in research. But we could not keep up to the pace. That is the reality. And that is where I think government policies are going to be extremely essential. This is something, I don't know whether we have realized it. This is something we got to do. Otherwise, even if you make a fab, who will buy those chips? Of course, if Intel comes and makes the fab, Intel has the customer and it's very easy. It's a no-brainer.
No, I think this should be mentioned because I was involved with the NavIC discussion with the government, and we actually did because we were using FPGA array, etc. And the government needed to put about $50 per person for the first million users, GPS. They refused to fund. So unless there is a subsidy to reduce the differential price the consumer has to pay for some time, the manufacturing base will never come up. So that is a larger investment than the fab manufacturing is my suggestion.
Go ahead, Pranay.
Yeah, but one new sector of demand is the mobile phone assembly, which is happening now in India, right? So now Apple, Samsung, etc. are, through their contract manufacturers, are trying to do that in India. So probably that is one new demand function which has come in, which wasn't there in the past. So that is one. And yeah, maybe for 5G chips, etc., we'll still need those.
I think also on that same front, the next big mobile phone equivalent will be IoT. Basically, the IoT stands for Internet of Things. So you want to be able to turn off your lights remotely. You want to be able to turn on your microwaves remotely. Those are simple examples, but there's actually lots of examples in healthcare, agriculture, things that really matter to a country as large as India. This is a big next wave that's actually hasn't seen its crest. And so the pull will come from, say, large agricultural and healthcare industries where they say, look, I can reduce your healthcare cost, which is a huge cost. I mean, no matter which country you are in, healthcare is a huge cost. If you can reduce the healthcare cost by 5% using IoT, that's worth it. And so there are going to be new demands where anything that is not automated today will be automated. And IoT is the path to that automation path. And so the next generation of fabrication and packaging and testing and all of these will go through this IoT path. Particularly, I think that's where we are going to go through.
I'll do a very quick.
Please. Then we'll take the next one.
If a fab is set up and if the government has to subsidize to bring down the cost so that it can sell, it will never succeed. You have to build a fab which can be competitive in the technology worldwide. Otherwise, there is no way it can sustain. So the pull factor is only when you know what you're building, what your capability is, and which market chips that you're going to address. Any other way is temporary and artificial because it's not sustainable.
There is a small difference though. I mean, you should go back and read how Taiwan started the manufacturing facility. 100% really was government support. He said temporal, it is indeed true. It is not forever, but initial condition is extremely important. And that is where the question becomes important because there could be pulls in terms of applications, but these chips could be made by anybody. If Chinese fabs are subsidized 100%, those chips will also come in here. And the system builder will not care whether the chip is coming from Indian manufacturer or somewhere else. I think that is a very important point we should not lose sight.
I think what Sanjay is saying is you have to do it like gas pricing, where the pricing is a global price for that item, and then maybe you use Aadhaar-enabled payment service that gives them a subsidy for a certain amount of time, exactly like the Ujjwala scheme works or something to that effect. Because if you embed the subsidy in the price, it completely mucks up the economic system. I mean, the price is the biggest signal that an economic system can give. So, next question.
Yeah, my name is Buddha Bagai. I'm not from the industry. However, I did work for Analog Devices in America. If anybody is here from Analog Devices Bangalore, I'd like to meet him. That was 50 years ago. Now, my question really relates to the fact that there's a lot of criticism of the subsidies, billions of dollars that will go into fabricating semiconductor chips and all here, while there are other priorities waiting, poverty alleviation, education, employment generation. Now, when you talk about automation is necessary and coming, what is it going to do to employment generation in India? And of course, it's good to hear that the government is encouraging for the first time. I mean, I got an article from Ashok Parthasarthi, who used to be the tech advisor to Indira Gandhi, and he was very frustrated because his plans were all derailed. Now it seems that we are more serious about it. But how practical is it in terms of denying the poverty-stricken population, the employment generation, those aspects, education and so on? Can we not continue with foreign companies coming here and help them design and go about it in a more of an industry fashion instead of the government putting all their money into it and subsidizing at such a huge level?
Quick answer. We're going to take the next question. It's a little bit beyond the scope of this panel, but Pranay, go ahead on priorities, I guess.
Yeah, no, I mean, this is a question which can be asked for space, for defense, for many other things, right? But I think the point is important that there is an opportunity cost for government putting 1 rupee. Every rupee that the government puts for something, it costs rupees 3 to the society in India, right? So yes, it should be a concern, but it doesn't, I mean, these are some basic capabilities that you would have. I mean, if we would have thought on this lines, we will never have a space program, we would never have good defense facility. So I would agree that we don't need to spend all money on fabs, and that's where I would have opposed. But the good thing is that it's not just on fabs. We do need to take advantage of our strengths, and as long as we are doing that, then we are building employment, assembly will generate employment, design will generate employment, everything will have a positive effect as well.
I just want to give one statement on that. The same questions were raised when the space program was started. And what Vikram Sarabhai said at that time, that I want to use space technology for village upgrades.
Yes. So we'll debate this question perhaps after the panel, but go ahead, please, sir.
Yeah. Actually, the answers I was looking for have been raised already. Most important thing is, if you don't study the past, you will repeat it. So let's start with Chandigarh. It was established to bring self-reliance. Sorry, I have to introduce myself. I am Soundar Rajan. I had 4 decades of experience with DRDO and our dream was to look at components because they were very difficult to get components. So in all their wisdom, years back, 30 years back, DRDO and others worked together to start this Chandigarh thing. And what happened to that? The reason is, it's not because it's burnt. There were no users. When you make a chip, just now the question came and you answered. Raised, yes. Exactly. So I don't want to go into that. So we'll have to study where the application comes. For example, recently we were looking at most important semiconductor for us is the gallium nitride for the services because it both in the radar and electronic warfare technology, everywhere communication. So who will use those chips in India? You make a gallium nitride. Of course, IISc is leading it now. Well, who is going to use? So if you take the lower end of that, you go to the low power, high power, low frequency applications where power supplies and whatnot. Who are the guys? Tatas are going to make EVs. Are they going to have a lab which design the circuit, the motor controllers or engine controllers, everything, and then use this? No. In our experience, they are going to import it from somewhere.
Got it. I think your point is valid, and I will integrate it with what everybody else has said, which is that demand fitting into the ecosystem is a very important part of the evolution of the industry in India. And I think we have also added that you can't artificially keep a price for too long. You have to find a way for that price to actually work. And the only way all of that will work is if the technology is competitive in whatever it is that you choose. The reason why Maruti works is because in that segment, it is competitive worldwide.
The second point is, if you look at the CHIPS Act, which came recently, where the Americans who were totally anti-subsidy, pure capitalists, are putting money in that, the reason is self-reliance in defense and critical infrastructure. So they want cyber security the highest aspect. That is why they say they don't want even to believe another factory in US doing the manufacturing. They want to control everything. Now, when we want to do this here in India, we are going to put 50,000 or 70,000 crores. We are going to use the CAD devices coming from US. The basic chip design, circuit design is brought out. We are not having any of those facilities with us. We are going to import everything. Now, if you look at the cyber security aspects of the hardware, it starts from the design, even before design, then fabrication, packaging, and many other things. So we are exposed anyway. So when this is my suggestion. I mean, I don't have a solution, but we'll have to now invest in those design tools as well. I don't think anybody is talking about it. And it's a very difficult thing because a design tool is made by a designer over 50 years of experience. It is not.
Got it, sir.
Thank you.
Last question, since we have a tradition of ending on time as well. Is there one more? Two more questions, but quickly, please.
In continuation with GPS versus Navik, the demand is there because the ISRO has given the RFP for millions of ICs. Apart from that, from the security point of view, many of the military equipment, they work with GPS. Tomorrow, if the GPS satellites are cut off, we will not be having the required location navigation basis. So at least METI gave two companies 2 years back a sort of funding also, but we are proud of our designers. But till today, I understand that there is no indigenous, whereas most of the Chinese mobile phones have already incorporated Navik. Why is it that we are failing in India?
Anybody want to answer that?
take the last.
I think there's no satisfactory answer to that question.
We want to know as well.
Yeah, we want to know as well.
Hi, my name is Mayur. So I work in semiconductor industry. So I work in many fabs and even test and assembly plants. So let's assume that we establish manufacturing here, right? So one of the main problem in manufacturing is getting the utilities, electricity, water, and the second part is disposing of the harmful chemicals and cyanides and even stuff that we use. So as a policymaker and the guiding to the government, what are we doing if we achieve our dream of manufacturing to still say carbon neutral and not to dispose of our environment, which is very easy to do in our country, as sorry it is to say. So as a policymaker and advisor to the government, what are we doing against that?
But
Yeah, so, there are technologies available to have a zero waste disposal, right? The chemicals can be treated, the gases can be scrubbed, all that is done. I mean, you should actually, if you've not visited a fab, you should do that. In fact, silicon manufacturing, touch wood, is one of the, industries you don't really hear about, all these, violations, like, a coal industry, for example. Right. The reason for that is there is a very strict adherence to the guidelines, right? The guidelines are extremely strict, and they have to be done. And the other question that you asked is water and power. And, again, it's not difficult. We had made an assessment, again, 15 years back, that in a location near Bangalore, we had said that if you just do the rainwater harvesting, that water is more than sufficient for your requirement, right? So there are these new ways of looking at this problem. And, rainwater harvesting is a no-brainer, which we are not doing anyway, right? There are things like that which can be done, and, it's not a rocket science.
Just to add to your point, like I have actually worked with many of the companies that you listed out in your presentation, and we have seen actual cases in Taiwan where the assembly lines are shut off by the government because there's cases of indisposable chemicals in the river there and all that. So, and even to the level that even in Bangalore tech parks, when we run out of electricity, we cannot even support that electricity, and we have generators powering those plants, which is too much non-carbon neutral. So to me, what you're saying is true, technology exists, but I don't see practicality in our country right now. So how do we make sure that happens as a policymaker? Like that's the question I want to ask. I know the technology exists, I work there as well, but as a policymaker, what are we doing to make sure the investor is doing that, right? So that's the question I want to ask maybe the policymaker.
we'll end on that note. The next panel will be on market solutions to pollution. So thank you very much. Thank you all for coming and listening.